Hello, today I will be presenting our paper titled Camera Motion Generation Method based on performer's position for performance filming. Filming live performances come in various forms, such as shooting for music programs and music videos. In recent years, the chances for filming have increased due to live streaming of performances and the release of video products. In filming, camera work becomes an essential element that characterizes the video. The footage on the left shows the scene during a performance shoot, where you can see the cameraman moving around on stage with a camera. This cameraman is famous for vigorously moving the camera in sync with the choreography and singing, capturing distinctive footage during performance filming. The filmed footage looks like what is shown on the right. You can see that by moving the camera in tune with the performer's movements and varying the speed, they aim to capture footage that conveys the charm of the performance. In this way, cameramen consider the performer's movements and direction when filming. However, since camera work is a type of video expression and is often determined based on experience, designing a standardized camera work that can be used for any performance filming is difficult. In live performance filming, there isn't a specific reference like storyboards. Instead, camera work is considered through stage scripts and rehearsals before approaching the performance filming. During the actual filming, performances can't be restarted from the middle. The choice must be made regarding which filmed footage to release. The goal is to create a better video product from the limited footage available. To produce a video that adequately conveys the charm of the performance to the viewers within these limited filming opportunities, pre-examination of the camera work becomes even more crucial. The stage script, or live progression script, includes information on the performer's positions during a particular scene of the performance, details related to sound effects and lighting, as well as other production elements, and information about lines or lyrics. In this study, we consider using the sparse, chronological performer position information obtained from the progression script as the performer position information at keyframes during the performance. With this, we aim to automatically generate camera work. In this study, by utilizing deep learning to capture the implicit knowledge of camera movements corresponding to the performer's movements, we worked on automatically generating camera work suitable for live performance filming. In other words, from the performer's position information on stage available before the performance, we want to generate the trajectory of the camera, which can be used as a reference for live filming. The flow of automatic camera work generation proposed in this study is illustrated in the figure. It extracts the performer's position and orientation information during important scenes, or keyframes, from the script. Based on this, the system consists of two stages: the keyframe camera network, which generates corresponding camera positions and orientation, and the camera trajectory network, which produces the entire performance's camera work from the performers and camera's positions and orientation at keyframes. To simplify the problem in this study, we considered only one performer and excluded information regarding height, camera roll and pitch, focusing only on the position and the direction on the stage. The goal of the keyframe camera generation network is to generate camera positions and orientation for key moments in the performance, such as the beginning and stopping points, which are the keyframes of the performance. The network uses the performer's position information and body direction from the keyframes obtained from the progression script, as well as the frame number representing the timing during the performance, as its inputs and outputs the corresponding camera position and orientation. The loss function for the keyframe camera generation network is made of four terms. The first term is the error of the distance between the performer and the generated camera. The second and third terms are the errors of the generated camera position and orientation, respectively. The last term is the error related to the camera's relative distance between the neighbor frames. The purpose of including this term is to let the network be able to learn the big movements and generate more dynamic camera motions. The camera trajectory generation network aims to fill in the camera positions and orientation between keyframes and generate the entire camera work for the performance. The network uses the performer's standing position and orientation information from the keyframes, interpolated using a spline curve, to obtain a virtual representation of the performer's standing position and orientation information throughout the entire performance. It also uses the camera positions and orientation generated by the keyframe camera network for the keyframes, the frame number indicating the timing during the performance, and a keyframe flag token that indicates whether the input frame is a keyframe. Based on these inputs, the network outputs the camera positions and orientation throughout the performance. The loss function for the camera trajectory network is made of three terms, which are the camera performer distance loss, camera position loss, and camera orientation loss. Each term is the same as those in the keyframe network, except that the interframe camera distance loss is not included. In this research, we used data from MMD, a 3D CG animation creation software, as the dataset for live performances. From music video works using MMD available online, we collected motion data for performers and camera work. We then performed pre-processing normalization on the three-dimensional positions of the collected character and camera motion data. By mirroring each motion data left and right as a data augmentation, we constructed a dataset consisting of 96 training data and 4 evaluation data. In this research, we constructed a network based on the transformer for generating camera motion. Regarding the position embedding method used in the transformer, we verified the difference in camera work learning due to the difference in position embedding methods. Two approaches are compared in the experiment, the original transformer and a relative positional representation transformer. The vanilla transformer embeds the ordinal interframe relationship from the starting frame, while the relative positional representation transformer embeds the ordinal relationship with surrounding frames, by adding a learnable matrix to each attention maps, allowing attention to be informed by how far two positions are apart. Apart from the difference in the position embedding methods, the same network design was used. The result of plotting the camera work generated using the performer's position information from the evaluation data is shown in the figure. The figure is an overhead view of the stage, where the green points represent the performer's standing position, and the points changing from purple to yellow represent the camera's position. The purple in the camera position indicates the beginning of the performance, and as the performance progresses, it changes to yellow. From the left, the figure shows the results of positional representation transformer, vanilla transformer, and the ground truth data. When examining the generated camera work, the vanilla transformer generated similar camera work for data 1 and data 2, even with different subject movements. In both cases, it depicted a continuous camera work regardless of the motions of the performers during the performance, indicating that it couldn't effectively learn to move the camera according to the performer's motions. On the other hand, the RPR transformer generated different camera work for different performances, suggesting that it was able to learn camera work that corresponds to the performer's motions. Furthermore, in terms of the error regarding the camera position and posture for the evaluation data and the loss during training, the camera work using the RPR transformer showed better accuracy. This suggests that the position embedding method, which embeds the ordinal relationship with surrounding frames, is more effective for learning camera work than the method that embeds the ordinal relationship from the starting frame. To evaluate the impression of the generated camera work, we rendered them on Unity and conducted a survey on the impression of the footage filmed using this camera work. To compare with the footage generated by the proposed method, we generated 4 more footages, whose keyframes and camera trajectory are generated by different combinations of our proposed method, the spline curve interpolation, and the ground truth data. In this evaluation, we had 20 participants. Participants were shown 2 videos for several rounds, and in each round, they are asked to evaluate which one they preferred on a 5-point scale. Based on the results obtained from the survey, we conducted an analysis, using Sceffé's paired comparison, also known as the post hoc test. The average degree of preference for each video is represented in the graph. As can be seen from the graph, footage using the ground truth keyframes tended to be evaluated with a higher preference. Regarding the camera trajectories, footage generated by spline curve interpolation had a lower average degree of preference than footage generated by the proposed method. Here is the conclusion. In this study, we proposed a 2-stage camera work generation method that can be applied during the filming of live performances. We collected datasets for live performances, consisting of both performer and camera positions and orientation from 3DCG. We compared transformers that embed the relative positional information with surrounding frames and transformers that embed the absolute positional information. It was confirmed that embedding the relative positional information is effective for learning camera work in our method. The result of the subjective evaluation showed that footage using the ground truth keyframes tended to have a higher average degree of preference for the subjects, while footage generated by the proposed camera trajectory network had a higher average degree of preference than footage generated by spline curve interpolation.